Hi, my name is Venkat. I work as a senior architect at Razorpay, and I have with me my colleague Srinidhi, who works as a lead engineer at Razorpay. Today, we would like to talk about our open source offering called DevStack and some of the interesting things that we have done atop DevStack. The title of our talk called Befriending the Cloud with DevStack. We talk about remote debugging, we talk about data capsules, and we talk about a lot more. Who are we? Razorpay is a full stack financial ecosystem and a banking suite for businesses of all kinds and shapes. Today, we have millions of businesses that depend on us to move money in the entire country. We work across every single leg of money, which is in terms of accepting, processing money, and disbursing money. We're very proud to say that we are one of the largest money movers in the country. We are also acting as a banking hub for all our businesses, and we also work as a neobanking partner with a variety of our merchants and customers. A lot of our interesting work is captured on our blog, which is engineering.razorpay.com. With that, we quickly walk into some of the interesting problems that we have at scale, not just system scale, but human scale, developer productivity problems, and how we are trying to solve this through our open source offering called DevStack. A good introduction about where we come from is Razorpay has been the first organization in the country to have gone in with a production-grade Kubernetes infrastructure much before any of the managed offerings like EKS, etc. existed. Somewhere around late 2016 to 17 is when we've moved our entire infrastructure into Kubernetes. Now, as we moved into Kubernetes, while Kubernetes solves a variety of interesting problems, cloud-native development with Kubernetes specifically comes with its own set of challenges. Let's start with some interesting problems. First is, how do we develop and deploy code? So typically a developer writes code on their laptop, checks it into Git, raises a pull request or a branch and checks it into GitHub, at the end of which maybe there is a GitOps pipeline that kind of runs, which builds the image, a Docker image, for instance, and then they use some deployment tool, which could be Argo. We use Spinnaker, a variety of deployment tools. Now, the problem with this is every single commit goes through this entire process of local development, building the image, deploying, build, develop, deploy, right? This entire cycle happens. Now, the other challenges that come along the way is that every single service also has some dependencies. For example, maybe a queue like Kafka, it could require a database like, I don't know, MySQL, maybe a cache system like Redis. The next set of problems, so how do you really stitch the application and the requisite infrastructure of all of these things? How do you provision them? How do you manage them? That's the next challenge. Once the code is deployed onto a pre-production environment, and just for reference, we are not talking about production workloads here. We are always strictly talking about development workloads, pre-production workloads, staging workloads, beta workloads, various different nomenclatures to this. So once this code is deployed to some pre-production environment, how do you really debug the code? Tons of challenges. You might have to enable logging, you might have to enable monitoring. What do you do really on local debugging in terms of even printlns in typical compile languages like Go, Java, etc. Again, it's a build development process. How do you really do good remote debugging as if you're debugging locally? That's an interesting challenge. The development process itself, in terms of the IDEs that you choose, different people like different kinds of IDEs. Some IDEs have licenses. How do you really share, exchange good editor conflicts, good development practices, faster ways to write code, develop IDE hacks, etc., etc. So all of this becomes next set of challenge. And last but not least is the cost. Because you're talking about pre-production environments, you don't have to keep this environment up and running all the time, which means that you really deploy code, you test it, and you want to really turn it off very, very quickly, which makes this largely ephemeral. And how do you really optimize for this in a very clean, nice way? Additional problems that come not just at system scale, we're using this word called human scale, which is as organization scale with engineers, additional set of problems comes in. One particular problem that kind of comes in is, as we mentioned, we cannot have infinite pre-production environments, which basically means there is a increased time to roll these features because there is a shared infrastructure, which is the last point. In fact, we cannot actually have for hundreds of developers and hundreds of services, we cannot have 100 different pre-production environments. That's going to be very cost prohibitive, and it's also going to be operationally complex to do that. So which basically means that you have one shared environment. And I'll just quickly jump to the next slide, and probably we can come back to what we are talking about. Maybe there is, imagine what we see on the left-hand side. You have one shared environment, which we call as beta, which is the block, the colored blue block here, in which multiple devs and multiple applications could reside. For instance, there is a developer called dev1. Maybe that developer is using, let's say, 3 applications, which is basically an API application, maybe a dashboard application, and a cards application. Similarly, there's another developer called dev2, who's probably also using their own version of an API application, their own version of a dashboard, and cards, maybe 2 different branches, for instance. Now, pretty much for all of these developers to work on this shared environment called beta, and you could have probably finite number of such environments, the process kind of roughly looks like this. The developer goes and somehow reserves an environment. They deploy their code, they test, release, reserve, deploy, test, release. This is a very sequential process. It just scales to the number of environments, and it's a very sequential, non-scalable way. This is what we have realized as we've grown. Now, can we sort of really, flip this whole thing, where we can actually create for every single developer a slice of this infrastructure, and this entire suite that we call here, right? This entire collection of applications, in this case, let's say API, dashboard, and cards, for example, is what we call as a service fleet. So every developer could actually have their, part of this entire infrastructure where they could go ahead and deploy their service fleet. And as you notice, different developers in this case have different kinds of service fleets, depending on what part of the application or the stack that they're working on. And this makes it completely parallel. It's completely independent. The developer doesn't have to depend on anyone else. The developer can actually go ahead, do their own work, and release the environment, and all in a cost optimized fashion. So that's the first part of the problem in terms of this one. The second part of the problem is as we grow with scale, and as we grow with containers, and as we go with microservices, there are a bunch of microservices. There are also mock services that you need to kind of build corresponding to that. For example, in our world, we deal with a lot of banks, gateways, etc. We can't have that setup available in our dev environment, which means what we really do is we actually have a mock HTTP gateway, a mock bank gateway of sorts that which we hit, and then that's supposed to send back an equivalent response that allows developers to build and test. So these services are also finite. How do you sort of really scale them? So larger scaling problems, both at human level as well as system level, arises, which is exactly why we went with DevStack, which I explained as the principles. Now, how did we go about building DevStack? Simple open source tools and some amount of code that we had to do. So the first part of the problem, like I said, is a service fleet, which is a collection of services that is useful for a developer. How do you sort of really orchestrate the service and the service dependencies? We use something called Helmfile, and think of Helmfile as nothing but a Helm chart. Just as a Helm chart specifies the dependencies, a Helm file declaratively allows us to specify service level dependencies, which are not really Helm charts, but actually application service level dependencies, and also associated things like database, queues, secrets, config maps, whatnot, right? So that is what Helm file does. Now, typically to execute a Helm file, and Helm file actually, as the name suggests, uses Helm, we also extensively have built and leverage Helm hooks. For instance, let's say an application, in this case API, for example, requires, let's say a config map, or it requires, let's say an SQS queue or a Kafka queue. The Helm hook basically pre-provisions this Kafka queue or pre-provisions an AWS resource before the application starts up. Maybe as application health check, it goes and checks whether Kafka is up. So it really pre-provisions this Kafka queue and goes ahead and then goes ahead to deploy this application. Now, the third leg is, again, there are a lot of scenarios where we may use a very cloud specific tool. Like in our world, we are on AWS, we use SQS, SNS. It's humanly, again, impossible to maintain and manage hundreds of SQS endpoints or hundreds of SNS endpoints. So pretty much what we try to do is the mock part of it. We leverage something like local stack, and we believe that there are equivalent in other cloud providers. So local stack allows us to mock these AWS specific endpoints. So as part of the Helm hook, when you're saying use an SQS queue, all we simply do is we actually do a local stack deployment and say, hey, here is the SQS endpoint, which we then configure it via the environment variable, via config map, or pass it through the deployment environment variable, etc. So typically a Helmfile workflow looks like this. The developer triggers a command called as Helmfile sync, which does a whole list of pre-install steps. For instance, It could be creating an AWS resource generation, or it could be spinning up a database. It could be, for example, cloning secrets or cloning config maps, because you have a base application from which this is cloned. Then you actually go ahead to do the actual deployment. But the most interesting part is that after the deployment, let's say I have an endpoint that I need called api-venkat.razorpay.com. The post Helm hook deployment actually goes ahead and creates an ingress like that for me, which means that, interestingly, all of this can actually be done by a GitOps workflow, which means I file a PR. At the end of the PR, as part of the PR checks, we actually go ahead and call an API that does all of these things, and then the response comes back saying that, hey, here is the endpoint for your PR. That's beautiful, right? Now, to do some of these things, in addition, what we do is that we need a way in which we need to header-based routing, because imagine this: I am having an application with a version v1, and my colleague Srinidhi is having the same application with version v2, and I want to make sure that my v1 talks to his v2, which means I need a way to distinguish v1 versus v2, and that is something that we use via header propagation. So we have niftily introduced ingress controller hooks within Traffic 2.0, which we can introduce in any ingress controller like Ambassador, Envoy, Nginx, any ingress controller that allows us to do this way of transformations. That can be done. To really propagate the headers, we use open tracing. Again, we don't really really deploy code, and what we actually do is that we use something called as dev space sync, which allows us to actually build the code. You don't have to go through this entire build and deploy lifecycle, and we actually say dev space sync. And all that it does is that it literally takes our code and syncs it onto the remote Kubernetes cluster without a pod restart, without actually going through an entire deployment hook or deployment model of sorts. So it synchronizes, for example, in a secure fashion. Of course, there are secure tunnels, etc., but it synchronizes nicely in a secure fashion. Last but not the least, we spoke about an ephemeral environment, right? And all that you do as part of Helmfile is you can set TTL annotations. And then we have used kubejanitor, which actually looks for these annotations. At the end of the TTL, it simply goes ahead and deletes the pod or deletes the application. And this is beautiful because now with a Kubernetes cluster, if you have a horizontal pod autoscaler and a cluster autoscaler like what we do, you deploy the application. If there are no nodes, HPA scales the application. The cluster autoscaler realizes there is no node. The cluster autoscaler automatically attaches node to the cluster. Applications run. At the end of the TTL, kubejanitor goes ahead, terminates the pod. HPA brings down the pod. And as HPA comes down, cluster autoscaler comes down. And you have a really cost-optimized way of doing this. We have an interesting presentation that we have on Kubecon talk that is attached here. I would strongly request and recommend that as the audience, you would want to probably go through that, because I've just given a quick recap of what we have done. That has got a lot of details. I would strongly request that you go through that before you can jump on to the next section, because every principle that we're going to talk about is actually built on this solid infrastructure that we're talking about. So it'll be kind of confusing if you don't understand some of the primitives. And in the interest of the talk's time, we have not added all of those things because it'll be a really long talk. With that, I hand it over to my friend, Srinidhi, who will walk you through some of the other interesting things that you have done atop this.
Thank you, Venkat, for briefing us about DevStack and its initial offerings. Let's now look into the features that will enable our developers to befriend the cloud even further. Remote debugging is one such important thing. What are the general problems that developers face in their SDLC? With microservices adoption, debugging scenarios involving them would not be feasible in local system because of the limitations of the system and also the complexity in setting up the entire services in their system. Replicating an exact scenario similar to what has happened in cloud is difficult in local because of the small data set at which the tests are running. The typical standard mechanisms of adding println and loggers and analyzing them via logs or metrics platforms like Sumo Logic or New Relic is cumbersome and time consuming. So what could be the solution? So we will have to enable developers to have the debugger connections come to their local system and work as if it worked on cloud. We have a couple of solutions that we have experimented and brought into practice based on our tech stack. So one for PHP and the other one Golang. So let's now look into how well the solutions fit in. For PHP, we would install xdebug in the Docker file, and then we'll also expose a unique port for debugger to listen to. We then route the debugging connection from the cloud into the local machine using DevSpace reverse port forwarding. In our IDE, we'll also do the configuration to accept the connection and then debug. The Go solution is not different either. Instead of xdebug, we use delve in the Docker file and also expose the unique port. In case of Go, we'll have to build the binary with GC flags, which will build the binary without the optimizations. The same setup of routing the connection from the cloud container to the local system is also needed using DevSpace port forwarding. The setup of the IDE is also required here to debug it. Let's now jump into see how it works in real world. So we run devspace dev, which is the command that will enable us to create the ports. What this is doing is it's trying to replace the port, sync the code, and also open up the ports for forwarding. While this is running, let's look into the file that will enable us do the port forwarding. There will be a file called devspace.yaml, which will be used while for running devspace dev. So as you can see, this is the configuration. So we would have a forward port and a remote port, which will enable port forwarding. And also in the logs, we can see that there is a devspace helper that is being injected into the pod. The port forwarding is now complete, and also the helper is being installed. As the next step, let's go into the pod and see what is happening inside and also connect the delve process to do the debugging. We exec into the pod using the command kubectl exec, the pod name, the namespace, and the bin/sh. So once we are into the pod, let's look into the processes that are running. So just take a notice of another process called compile daemon, which is used for hot reloading. So compile daemon will build the binary with -gc flags, which will disable optimizations. The process 1715 is the one that is serving our request, which is running ./bin/app with the env as stage and also the base path as app/router. So in the delve command, we attach it to the process 1715 in this case, listen to the port 3000, and also have headless with API version and couple of other flags that will optimize the port connection. So accept multi-client and also --check go version will be set to false. The moment we run this process, delve will be watching through the port 3000. The next step is to configure our IDE's debugger to listen to that port. So we'll have to go edit configurations, provide the port as 3000, which is already exposed via devspace dev. So once we start the debugger in debugger mode, we'll get a notification that it is connected. Let's now go into Postman and hit a request where we want to debug this. So this is a particular request that we are trying to hit, which is equivalent to stage, and we're trying to debug the same. So as seen, the debugger has now stopped in the breakpoint that we have configured. We can now look into the parameters, variables, and develop as if we are developing in the cloud ecosystem. All the cloud requests via this will be available in the developer laptop to debug, to see the data and make logical decisions on where and what the failure is. Let's now move into the next feature that will enable us complete the entire ephemeral infra puzzle. So ephemeral databases, or databases in fact, are a critical part of any application. So having databases ephemeral will be a primary requisite for the application to be ephemeral. So before jumping into the solution and looking into what the implementation is, let's look into the attributes that will define an ephemeral database. The first one is pre-populated database, which will contain the representative or identical data similar to the golden database of the application. The golden database here could be a stage 1 or a pre-production database. The second attribute is that the database needs to have the schema that matches the golden database and also enables the developers to run the migrations on top of it. The third one is that the database should be spawned, reset, or terminated easily. We should not have any dependency or manual intervention from DevOps, DBA, whatnot in order to provision or run these ephemeral databases. The last one, but not the least, is that the database configuration should be easily done by the developers, and also the access should be easier so that the developers by themselves can perform any DML or DDL changes. So what are the prerequisites for enabling ephemeral databases? So in order to have the data set, a pre-populated data set, we need backups that are supposed to be done. So what we have done is that we have set up Kubernetes cron jobs that will run periodically and take backups. So these jobs will run through the databases that are present inside our golden data set or a golden database host, which could be a stage 1 or a pre-production one, takes a data dump, uploads it to S3 with the appropriate tags. Users, while running Helmfile sync, can specify the version of the backup that they want to like. But the limitation with this particular S3 approach is that for databases with larger data set, the seeding may take time, which will hinder developer experience. So the solution for that is data containers. So data containers are created directly from the backup files that are generated in the data backup mechanisms. So we bundle all of this data in a Docker file, tag it and push it in order to consume data. The benefit that we obtain from this is that the time consumed for seeding is not required. So these data containers with versioning will also help developers choose the data that they need to run their application with. So for example, a container could be a MySQL base image of 8.0 version and then a DB volume of a particular date that is snapshotted. So we would tag that as data container MySQL colon 8.0 hyphen with the date. So on running Helmfile sync, the developers can get this data as their data set. So let's move into the database provisioning, seeding, and migrations, which are core of ephemeral databases. So we extensively use Helm hooks here in this case. So at pre-installation, there will be a database provisioner that will run and create the database. So example, it could be a MySQL container, it could be a Postgres container that the provisioner will create. The seeder will now pitch in to download the S3 and inject it to the freshly created instance. We can use data containers as well directly to avoid this seeder step. The schema migrations that are specific to the developers can be run here using the migration jobs. The secrets of all of these, the database secrets, the passwords, etc., are fed into the pod using Kubernetes secrets. So we also use a Helm hook called secret cloner here, which will clone the secret and inject it, which can be consumed by the pod. So this is how the typical ecosystem looks like when we have multiple databases or multiple developers working with ephemeral databases. Let's now quickly jump into the demo of the same. So in this case, we have Helmfile, which has the configuration for creating the service fleet. So in this, we will specify different parameters like ephemeral database or dev stack label or the version and etc. etc. On running Helm file sync, the changes that are there in the YAML file will be reflected in our cluster. So in this case, we are using an application called governor with ephemeral database. Let's now quickly watch what all are happening in the cluster with respect to the ephemeral database. We just watch for the kubectl get pods in all namespaces with this particular dev stack label. So we grab ephemeral DB demo to see what's all happening. And as seen in the screen, there are multiple jobs that are running. The secret cloner has already completed and a secret updater is running now. So there is also a migration job that is being created right now. And if as seen, the MySQL ephemeral DB demo 59BB, whatever it is the MySQL container that is running with the data and the seeder is running. Let's look into the jobs that are there and take a notice of something called hook wait, which will specify the order in which each of these jobs are run. So there is a DB configurator, there is a DB seeder, there is a migration job, and also a secret updater. All of these are hooks with different weightages. So right now, there is the web pod that is coming up, which will talk to this ephemeral database. Let's just look into the logs of some of these pods to understand what they're doing. So we can check the logs of the pods by running kubectl logs. So we run kubectl logs kl with the namespace given in the command. So the MySQL seeder will have given the command, and this would have downloaded the file from S3 and sync the data. As the data set is small here, we are using the S3 approach instead of the data container approach. So this is the web application that is running, and as you can see, it is running probes and it's 0 bar 1 because not all probes are complete. The moment the probes are completed, the application will be up and running. So our helm file has now given the output, and if we access this resource, we'll be able to access the ephemeral setup of the application with a database which is seeded. With DevStack, enabling developers create ephemeral infrastructure parallelly, help them sync their local code and do hot reloading, also remote debugging to debug in local, and ephemeral databases to provide databases ephemerally. The next feature is around integrating gitpod with DevStack. So this enables us move the entire software development to the cloud. This particular feature is still in beta, and there are a lot of benefits that we are seeing already, and some of them are first being streamlined developer onboarding. A full dev environment can be created by just clicking a button and it would be ready to code immediately. Testing features will also be simplified without installing dependencies in the local system. So the benefits for a newly joined engineer by doing this is humongous. The second one is around providing continuous dev environments. Developers can now work on parallel features without stashing their chains. We all have gone through that phase where we stash changes and struggle with merge conflicts. With Gitpod and DevStack, there will be no need of stashing data. Remote debugging along with Gitpod will be a boon for developers where they can debug pre-prod like requests. The collaboration will also be easier because the developers can now share their dev environments directly with their peers for deeper reviews. Also, snapshotting this data and sharing with the testing team or the UAT team will now be very streamlined.
Thank you, Srinidhi. With that, we come to the last interesting part in terms of smart scaling. And like the Gitpod, this is also heavily experimental, which we hope to master in time. So while we are running our workloads, as I mentioned earlier, with kubejanitor, TTL, TTL is great. TTL is also TTL can also be abused, because at the end of the day, the Helm file is something that a developer can, keep with themselves, and they can modify the TTL. They can do variety of other things. So when the TTL gets abused, automatically, of course, the infrastructure cost increases. So what we really want is a way that allows us to sort of pause and resume, which basically in that sense is basically a scale down and a scale up way of doing things, but not just randomly, but on demand, which basically means that whenever let's take an example, an web application or a web pod is not receiving requests for a certain duration of time, we can say, hey, go sleep for a while, release the resources. Or let's say, for example, there is a queue processor that's not receiving queue messages, we can say, oh, sleep. And whenever a new request comes in, the pod has to automatically wake up and say, okay, now I'm ready, I'm going to serve these requests, right? To really do this, how do you know that a request is getting received? You need some metrics. We use Prometheus Victoria metrics. So you use some metric system, and based on the metrics, you basically decide whether should I remain alive, should I pause? And now imagine I paused a container in some fashion, and I want to wake up the container. At that particular point of time, let's say you're getting a request, you don't really want to time out those requests, or you don't want to really fail those requests, which means that you need to prevent some of these things. So what we are doing right now, we're experimenting this, and we have some interesting beta solutions for this. What we're using is again an open source offering called KEDA, or KEDA, whatever you want to, pardon my proper noun, but KEDA, which allows us to actually scale up and scale down pods based on metrics. Now, what are these metrics that we're talking about? As we mentioned, the ingress control is traffic. So traffic can emit metrics in terms of the number of requests it receives per unit time. If, for example, exactly like what we are doing, if we, for example, say within the sliding window, if you're not receiving requests for such and such a duration, go suspend the pod. And as soon as you start getting a request, go wake up the pod. This is something that KEDA can do. Now, when you're waking up the pod, like I said, at that point, if you're getting a request, what we are also doing is we have written retry hooks within traffic to actually go ahead and check through the service endpoint, which is nothing but a web, whether the pod is up. It just does a liveliness check. We've written a traffic middleware that just checks it. And then once the service middleware, once the service endpoint says that, yes, I'm up and active, that particular request is actually sent. Of course, there could be certain timeouts in certain scenarios that we get, client-side timeouts, for instance, if they are very poorly set. But again, hey, this is not production environment, this is development environment. We can try to reduce as much as possible the timeouts. We will definitely reduce the failures. Timeouts is something that we are still working on. One of the largest limitations that you've seen is, while all of this works great for stateless pods like webs or web pods or queue processors, the database thing, the ephemeral database that my colleague was talking about, how do you really scale down and scale up an ephemeral database? Because it's kind of a time-consuming process. There are not, to be fair and honest, there are not clean solutions that we have, but we hope to find some of those interesting solutions in time. With that, I'd like to come to the last section of the slide, which is in terms of some of the future things that we're trying to do. The first of these things that we're trying to do is, while all of these solutions sounds actually complex, it isn't very complex. It is a bunch of CLI tools, nicely woven together. Actually, just one CLI tool, which is basically the Helmfile or the DevSpace tool, which is nicely woven together. But one of the challenges that we have internally seen is, while it's great for people working on backend, always the question happens to be, hey, I'm not very comfortable running these CLI commands. I don't know Kubernetes, typically from folks working in the front-end domain. So it is sometimes nice to have a web-based interface and kind of create a SaaS offering, internal SaaS offering, open source SaaS offering. It kind of bundles and packages all of these things. That's one major future work that we are embarking upon. The other part of it is that while scale up, scale down is nice, we still see a couple of issues. We are exploring something called virtual namespaces which is nothing but a namespace, but that actually creates something called as a virtual cluster, which means that every single developer can actually go ahead, just using a construct of Kubernetes namespace, can actually go ahead and look at their namespace as if it's a physical Kubernetes cluster with its own API service, with its own API service. You could launch your own Prometheus, for that matter, and do a variety of other interesting things. This is again heavily under experimentation. The ephemeral database solves simpler databases like MySQL, Postgres, Redis, etc. Complex distributed database like Cassandra, MongoDB. How do you sort of solve that through the ephemeral databases? One side. The other side is that while our majority of our development is in PHP and Go, largely into Go, we do have some polyglot environments as well. Specifically, for example, in our data pipeline, in our data science. So it's a polyglot stack. How do you sort of really build the solution out for a polyglot multi-stack kind of a scenario? Last but not the least, while for many cases a system like local stack works great, as we are embarking on our journey with multiple cloud providers, also in certain scenarios like a performance or a pre-production performance testing, we cannot really just rely on just truly on ephemeral non cloud provider systems like SQS. We can't just rely on local stack. In which particular case we need to have a mechanism to actually leverage the same stack to pre-provision an actual AWS resource and turn it off also on time. This is not currently supported. This is something that we are again working towards. With that, I'd like to conclude our talk. Please do share your questions, constructive criticisms of any kind, anything that you want us to improve upon, anything that you think that is of relevance, anything that you would like to contribute and work with us, most welcome. So thank you so much for your time. We really enjoyed talking to you. We really enjoyed this presentation. We really enjoyed sharing what we're doing, and we hope it's beneficial to the community at large. Thank you.